So welcome back to our final day. I've got my final day of the workshop shirt on to help keep us, at least me, motivated and you motivated, and hopefully the fourth day of Zoom is still treating you well. I'm going to start by just sort of checking back in on a couple of topics that have come up in various forms from previous days, some thoughts on sensitivity analysis, and then the value of information, kind of delving a little bit more deeply into that, and then folding that into an application of adaptive management with probing. All right, so let's dive right in. What I've got here up at the top is a question from CR from one of the earlier days, asking a question in the Q&A about how common is it to explore sensitivity to the various assumptions or components of the Markov decision problem that we're specifying, specifically things like transition probabilities or the reward values. And I answered, yes, this is common and it's really important. And I thought it would be useful to spend just a moment to check in on that. It's not adaptive management itself. You could do this sort of sensitivity analysis while doing adaptive management. You can do it while you're not doing adaptive management, but it's good practice. And a general take-home lesson is to try at the beginning to set up your code generally to allow for this, where you're specifying parameters and then loops and vectors in a way that you can iterate over different scenarios or different alternative values or different models that you might be interested in, and then setting it up so that your results are saved in a way that you can look across those different options in an organized fashion. So that's something to always keep in mind on the front end. So just to give you a quick example, this was a slide I showed on the first day. Specifically, I wanted to check back in on this application of vaccine allocation. And it's an example of looking at the sensitivity across different rewards that you might be interested in, whether it's minimizing deaths, minimizing years of life loss, or minimizing infections, as we go about trying to figure out how we allocate scarce COVID-19 vaccines in the very first month that they become available to the general public. So this is showing our policy decision in these in the bar charts here. And then we're seeing the sensitivity of that result across these three different ways of specifying rewards. And then what I didn't show you at the time was some other output. And I'm not going to go into the detail of what all this output means, but just show it as an example of a way to kind of display some of this stuff. If you're interested, you can go to my website and there's some links there to follow if you're interested in particular in vaccine allocation, this particular problem. But again, in this display, we're looking across the three different kind of rewards we might consider. And what's plotted in a particular figure by the color is a level of vaccination for a particular demographic group, which is specified along the bottom there. So whether you're in the 0 to 4 or 5 to 19-year-old group and so on. But what I wanted to point out was we're looking at the sensitivity of our policy across here, I guess it's 9 different scenarios that involve alternative parameterizations relative to our base scenario. And visually just getting a quick sense of in what situations is our optimal policy really sensitive to a given scenario like the one pictured here. Another interesting way to go about this is to also ask the question of, suppose that you're assuming some sort of true scenario, which is pictured here along the horizontal axis. So we've got those same 9 scenarios laid out along the horizontal axis. And then on the vertical axis here is the particular policy that you apply. And the color here represents the degree of performance lost. So along the horizontal, or sorry, along the diagonal here, we have 0% performance lost because that's a situation in which the policy that we apply matches the true scenario. But off that diagonal, we have a policy that's being applied when it doesn't match the true scenario. And we see cases in which that doesn't have a big effect on performance, but then for certain true scenarios, like this one here, we see a potentially large drop off in performance if that's the true scenario and we apply the wrong policy. All right, so just wanted to share a couple examples there about thinking about sensitivity analysis, and there's an infinite number of ways to do this. Okay, so I wanted to switch gears here and dive a little bit more into the value of information, to think about that in a bit more specific detail. And then we're going to tie it into some adaptive management applications in just a moment. But I wanted to give more of a specific definition of it here. So in general, the value of information is going to be the value of taking an action with information minus the value of taking action without the information. So that's specified in a very general way. So let's be a bit more specific about what we mean by these terms. So in this case, the value, this is typically going to be the expected present value of that long run stream of rewards. And then by action, economists typically think about this as we're choosing optimally in these two cases, either optimally with information or optimally in the absence of information. But you could have some other heuristic that you've specified for the action being taken. It doesn't necessarily have to be an optimal action. But then in particular, what do we mean by information? And you'll see different formulations of this in the literature. So I just thought it was good to check in with this. And it was prompted by a comment that Paul made. I'd mentioned value of information in the very first day and gave a particular example. And Paul mentioned, well, there's other ways to think about it. And that's absolutely true. So one example is, what is the value of having perfect information? So suppose you, in this case here, the information that you're talking about is perfect information. So you say, suppose I have a decision maker. This decision maker knows exactly what all the parameters and exactly how the world works. How does that decision maker do relative to a decision maker who does not? And that's useful because that can show you what the upper bound is in terms of the performance of a particular manager, including a manager who might learn over time. So that manager that learns over time, they're never going to do better than this manager who has perfect information. So that can kind of give you a nice sense of what's possible. The way that I was talking about it on the first day was this alternative formulation where you have some information arrival process over time. That's not necessarily perfect information right out of the gate. And the advantage there is that that's typically going to be a more realistic model for what managers are facing. So just to bring back that picture from that whiteboard example from the first day, I had pointed out this expected value of information in this application was 19. And the way we got that was by looking at the value of taking action with information, which was over here. So this was the expected reward when we responded optimally in the second period. We took that optimal action A star, conditional on whatever information we received. And remember that that scenario was information arrives there before you make your second period decision. Okay, so that was the value of a manager who's taking action given some information arrival process. And then this comparative value here, that is the value of taking action without that information. That was the very first decision maker scenario that we looked at up top. And the optimal action in that case was to develop, and that's irreversible. So you stay developed. That generated a value of 210. So that expected value of information came from the value of optimal decision making given information minus the value of your rewards when you don't have that information, which gave us that value of 19. So that was a toy example, but there are other applied examples. So I recently worked on a paper with some folks at the USGS. The scenarios that we considered was, suppose you have a manager who is uncertain about a particular parameter. In that case, it was a parameter that informed the impact that a non-native species had on an endangered species that you were trying to protect, which I think that species now been relisted to be threatened. And the management problem is to try to figure out how aggressively should we be controlling this non-native species that's preying on this threatened species that we're trying to protect. Well, obviously a key parameter there is how intensive is the effect of your predatory species on that non-native species. And we considered a decision maker who doesn't know that parameter with certainty, but expects to learn that parameter some number of years into the future. So for example, 5 years or 10 years, and say, what's the value of having learned that, which gives them a sense of how important it is to invest in research that would help to produce that information. And then also, how does the fact that we're going to learn in the future affect our decision-making today? So that was a real-world application of that idea, which you can find in this particular paper. Okay, so I now want to kind of turn our attention back a bit more explicitly to adaptive management, and also tee up a particular observation on active adaptive management. And an important question that I think is crucial to keep in mind as you think about designing a particular analysis when you're considering whether to use active, whether you're considering whether to go after and analyze an active adaptive management approach above and beyond a passive approach. And this is going to also tie into a question posed by one of the attendees earlier. We're going to get to an example of a probing problem here in just a moment under an active adaptive management approach. One of the things that many of us who were working on active adaptive management problems in the early 2000 teens, including myself and Paul Fackler and several other economists and ecologists, was that when we modeled decision makers who were either a passive adaptive manager or an active adaptive manager, we did find that there were gains to active adaptive management, but they tended to be relatively small, which caught me by surprise in the particular research that I was doing, and maybe caught others by surprise. I think I'd had some chats with Bond from this paper, who was also kind of surprised by this. And one of the key things that we arrived at was this sense that an active adaptive management approach, which uses probing, that is, deviates away from what you would otherwise do if you were ignoring the value of information in your decision making. So you sort of deviate away from what you would otherwise do in your management decision in order to learn either faster or learn something different than you would otherwise learn if you weren't trying to probe the system. And so what we started with the observation that we arrived at was, in a lot of the problems that we were looking at, this particular one, for example, here was a fisheries problem that myself and Jim Sankirko were looking at, and then there's a shallow lakes pollution problem that Bond and Loomis were looking at, was our passive adaptive manager was learning about the uncertain element in the model just a little bit slower. And so if it, in your application, if your passive adaptive manager is going to learn the same thing as your active adaptive manager, but maybe just a little bit more slowly, it's likely that active adaptive management is only going to give you a relatively small payoff. And where active adaptive management is likely to give you a larger payoff, where this probing is likely to give you a larger payoff, is when that active adaptive management, that probing, is going to give you information that you otherwise wouldn't get, maybe just a bit more slowly, under a passive adaptive management approach. So that's some advice to keep in mind. If you want to do active adaptive management in your modeling, it's going to pay to think ahead of time very carefully about how learning happens in the model, and then maybe do some simulations to think about, is my passive adaptive manager going to learn about this, learn about all the things that might be relatively important on their own? If so, if that takes a while, that's probably going to be relatively fine, and your active adaptive manager isn't going to be able to do much more than that. But if you've got a situation where where your passive manager is not going to learn some things, is not going to explore in the right way, in the right sort of rooms, if there's sort of information you can imagine tucked away in different rooms, if that passive adaptive manager is not going to go explore those other rooms, and there's important information in those other rooms, and an active adaptive manager would think about exploring those rooms, then you're probably going to have a greater chance at a payoff from active adaptive management. Okay, so I want to dive a little bit more into an example of that, of this valuable probing in an active adaptive management case that's also going to give us some deeper perspectives on value of information pulled from a paper I worked on several years ago. The particular application here is a new one for us. It's inspection of international trade. So we've got billions of tons of imports heading into the US and many other countries annually. Those imports, especially agricultural goods, are bringing in potential non-native species that can establish and do some damage. We spend a lot of effort trying to inspect this incoming trade, but we're highly constrained in how much of the trade that we can actually inspect. So it becomes pretty important to try to figure out, how do we target these inspections? How do we, Iadine just mentioned that fruit flies are ruining her veg garden. I feel your pain, Iadine. So right, we want to avoid the next fruit fly for Iadine, so she doesn't have to work so hard to get her garden to produce. So a key detail here is that we don't necessarily know what the relative risks of all these different sources of agricultural imports are, but we can learn about those risks over time, and we learn by doing. So we're taking the management action of allocating an inspector to a particular shipment, which helps to uncover infected shipments and take those out and avoid allowing those to be accepted into the country and potentially lead to establishment of non-native species. So we're doing the inspection to mitigate this invasive species risk, but we're learning at the same time. So we're learning by doing here. All right, so I want to take a simple example in order to make things hopefully a bit more clear, and then to work with a simple mathematical model to get some concrete traction on this. And it's going to inform this basic trade-off of exploitation, that is taking management decisions based on current information to basically get the best immediate reward, versus doing some exploration, that is some probing, to take some alternative actions that might not give you the highest reward and expectation immediately today, but provide some value that will help you make better decisions in the future. So in this simple example, let's just think about Australian and Guatemalan oranges. So here we have, these are both for oranges. So we've got oranges from Australia and oranges from Guatemala. And suppose in your record of inspecting these shipments that you have already on hand when you're about to make your decision, you've inspected a lot of Australian oranges. You've found some of them to be infested. In fact, 26% of them. Alternatively, you've got oranges coming in from Guatemala, but you've seen many fewer of them and found one to be infested for an infestation rate of 25%. So suppose you're at the border and you're looking at a shipment of Australian oranges and another shipment of Guatemalan oranges, and you can do one inspection. You can choose to inspect one shipment or the other. Which one do you inspect? Well, if you're only going to do this once and you're not going to repeat this problem over time, you would choose the one with the highest immediate reward. That is the highest expected likelihood of finding and then being able to intercept an infested shipment. But this is not a one-time decision. This is a repeated decision over time, where we're going to gather further information that will fit into our database. And you can imagine being much more uncertain about this estimate of the infestation rate from Guatemala, since it's based on only 4 observations versus the 191 observations from Australia. So it's probably not controversial, probably pretty straightforward to say inspecting Guatemalan oranges today probably has a higher value of information because we don't know as much about Guatemalan oranges, and it'll help us make better decisions tomorrow. Whereas the value of information for for an inspection of Australian oranges, that's probably not going to provide us too much extra information because we've already observed that particular source many times over. But then the question is, how do we formalize this? If we inspect Guatemalan oranges today, should we keep doing that over time if this number doesn't change, if we still stay at a lower proportion infested? How do we think about that value of information changing as we continue to make observations? So let's put this into a simple Bayesian learning model context. And we could call today Beta Bernoulli Day in this workshop, because you're going to see a lot of applications of this Beta Bernoulli process, or Beta binomial, which you'll also hear. The only distinction here is that in a Beta Bernoulli process, we make one observation. And in a binomial case, we allow ourselves to make multiple observations in a particular period. Okay, so in a simple model of this invasive species risk, let's suppose that we've got this fixed underlying probability that a shipment is infested that we're concerned with. And we want to learn about that over time. So P sub J is the probability that shipment from source J is infested, and that source is a country commodity pair like Australian oranges. So we're supposing underneath the hood here that Australian oranges pose a fixed risk over time, that there's a fixed probability that any given shipment is infested, and we're going to learn about that risk through time, and we're going to model our current beliefs at any particular time about that probability that Australian oranges will be infested through a beta distribution. And the nice thing about a beta distribution is it's limited on the interval from 0 to 1, which is natural for this kind of probability. And the nice thing is that if we make one observation of a shipment of Australian oranges, that's a Bernoulli trial. It has some probability of there being a success, that is an infestation. So that's like flipping a coin. That's a Bernoulli random variable, a Bernoulli trial. And when we have beta beliefs to start with, and we make an observation of that Bernoulli trial, our updated beliefs are also going to be beta. So that's an example of conjugacy, where the distribution we have to start that is then updated after an observation follows the same functional form, that our beliefs are beta to begin with, we make an observation, and then they're also beta afterwards, although with updated parameters. All right, so here are some examples of the beta distribution. Yesterday, you heard the parameters being referred to, I think, as either A or B, or sometimes you'll hear the two parameters referred to as alpha or beta. I like to refer to them as the S and F parameter because that aligns with successes and failures. So if the S and F parameter of the beta distribution are equal, like in this 1 in 1 case or in the 25 and 25 case, then notice that that distribution is symmetric across the unit interval, and the expected value is going to be equal to a half. So we have a 50-50 chance of seeing either a success or failure on the next draw according to those beliefs. And that expression is just given by this function of those parameters. So the probability of a success is given by the success parameter divided by the sum of the two parameters themselves. And notice that as the success parameter is higher, we have a higher, our beliefs are concentrated at the high end, meaning we think we've got a greater chance of seeing a success or an infestation. And if the S parameter is relatively low compared to the F parameter, that is consistent with beliefs that P is actually very low, and we have a lower chance of observing a success the next time we take a draw or make an observation, say, of a shipment of those Guatemalan oranges. Okay, so I wanted to give you a bit more of a concrete example of how this might play out over some number of periods. So here's period T, and in period 0, this is just going to specify our initial beliefs. So suppose we start off with an assumption or some initial prior where our S and F parameter are both equal to 1. As we saw in the previous slide, that gives us this particular distribution here, which happens to be a uniform distribution for P on the unit interval from 0 to 1. So that's just arbitrarily chosen as a starting point. And then in period 1, we observe a shipment, say, of Australian oranges, and suppose we have a success. That is, we uncover an infestation. Well, then we've augmented our success parameter by 1, and that failure parameter stays the same. Now suppose we move on to period 2, and now we make an observation of Australian oranges, but it's clean. That is, we have a failure. We did not find anything. In that case, we augment our failure parameter by 1 and leave that success parameter alone. And then we can repeat this process across these 10 periods. And the distribution, well, so we've got our updated, what are called hyperparameters here as we continue to make observations. And those distributions here are plotted from period 0 through 10. So the thickest line is the last period. And so you can note a couple things that happen. When we start off with a relatively low concentration, that is the sum of this S and F parameter is fairly low, we have beliefs that are not very concentrated, that are really spread out. But as we continue to make observations, of course, the mean of the distribution is sort of shifting around. But notice that the spread is narrowing as we continue to make observations. As this concentration parameter grows, that is, as our quote unquote sample size grows, that distribution starts to narrow. And if we repeated this to infinity, it should completely condense onto the true value for P. So I see there's a fair amount of action in the chat, although I'm not sure. Somebody chime in and let me know if there's something that I should answer immediately. It looks like there's some answers being provided there. So hopefully that's good. Okay.
Mostly it's the panelists making things right. There's not
cool. Okay.
They're just making comment. It's a commentary.
The peanut gallery. Excellent.
Yeah, exactly. Right.
Excellent. Okay. So I want to go back to our original problem here of thinking about, do we choose, suppose every day we can choose to look at either a shipment of Australian oranges or Guatemalan oranges. Our inspection budget is 1 inspection per day, and all we can look at is either the shipment of Australian oranges or Guatemalan oranges. This is, of course, a vast simplification of the true problem, but it'll be one that we can get our heads around pretty quickly. So we know that there's this immediate chance of intercepting an infested shipment. There's also some value of information, but how do we decide how long to look at a source that has a lower immediate reward because we think it might have a high value of information? That is, how long should we probe, say, a source like Guatemala before we stop and just focus on the one that at least currently looks like it has the highest payoff? So this is an example of a multi-armed bandit problem, that just comes from this notion of slot machines having the nickname of a one-armed bandit. They have one arm and they steal your money. So we've got two arms here to consider. That is two options we could choose where you can pull that arm, make that inspection, get a success or a failure, get a jackpot or don't get a jackpot. I'm not going to go too deep into multi-armed bandit problems. It turns out that there is, in the simplified version I just described, there's this object called the Gittins index. It's not worth going into for us. If you're curious, you can check out a source down here. But the nice thing is that this particular paper here gives us an equation that we can use to understand what is the immediate exploitation value, that is the expected value of getting a hit, and then what is the value of information that comes from inspecting or pulling that particular arm, pulling that particular option. And that value of information is going to depend in part on our sample size. And I'll show you that in just a moment. So if we've made very few observations, the sample size will be low, and not surprisingly, the value of information will be high. Another interesting feature here is that this value of information is a function of the discount rate. If I have a very high discount rate, I put very little weight on future payoffs, and my value of information is going to be lower because the value of information comes from making better decisions in the future. And if I care less about those payoffs, my value of information is going to be lower. All right, so let's check this out visually. Up here, I just have this summary of the data you already saw for Australia and Guatemala. And on this first figure, what I have plotted is this immediate reward, this expected value of exploitation of either the Australian shipment or the Guatemalan shipment. And remember, the Guatemalan shipment was just below that of the Australia level of risk. And then I've plotted the value of information for looking at a Guatemalan shipment and how that changes as the number of Guatemalan shipments we look at increases over time as we make more and more observations of that particular option as we continue to probe. And note that the value of information starts high and then it starts to fall in this concave fashion. So we get diminishing marginal returns, diminishing marginal value of information for further and further observations of that less well-known risk. So we put those two together, and this basically tells us that it makes sense to continue to probe and look at those Guatemalan shipments because that value of information tips the scale in that direction until you get maybe about 45 more shipments or so inspected. Now, of course, this is all holding fixed this particular estimate of the risk from Guatemala, and almost certainly in the real world that number would go up or down depending on what we observed. But hopefully this gives you a sense of thinking about how that value of information would change as you continue to learn. Okay, so is the VOI for observing Guatemala high enough to probe at least once? Yes, we have a high value of information to start with. When do we stop probing? Well, if we hold the estimate of risk equal after that many more observations. All right, so I want to switch gears here and talk about a very different element, and that is this challenge that we run into when we add belief states to our model. And as you've been doing in the breakout groups, notice that we've been adding those belief states against a backdrop of some physical states. For example, in the harvest problem, that population of fish either being in a collapsed, medium, or high stock level. But when we start to try to capture all of this stuff together, in some of the problems we face, the state space can get quite high, especially if we've got continuous variables, continuous state variables that we want to do justice to. So this can lead to what we call the curse of dimensionality. That is our ways of numerically capturing those state variables within software, say like MATLAB, like we're using, when the state space is so large that the solution techniques get bogged down. Either the processing power or the memory of your computer starts to get challenged by the size of your state space. So I want to just briefly introduce you to some emerging methods from machine learning falling under this umbrella of approximate dynamic programming, or ADP, that allow us a way forward. These are going to be helpful in adaptive management models and also non-adaptive management models if they have large state spaces. In some literatures, these techniques fall under some other umbrellas like reinforcement learning or neurodynamic programming. As an example, here's a paper I worked on in the last couple of years. It was not an adaptive management problem, but it shared some similar challenges where we had a 6-state variable system. So in this particular research project, we had 2 salmon stocks on 2 different rivers that converged and met in the ocean. So these salmon, here's my happy salmon. This is like the absolute worst real-time artwork here. That sounds a little bit better. So we've got these 2 different stocks or subpopulations, metapopulations, that are in this freshwater river system, and they converge and they mix when they outmigrate in the ocean. And to make a long story short, some practices that we've implemented over time, like hatcheries and impinging on their habitat, there's some hypotheses that is homogenizing these stocks, and thus their genetics are becoming much more and more similar over time. That the fish are becoming much more and more alike. So to capture this system, we needed the stock size for both populations, and then a mean and a standard deviation for a genetic trait that we were interested in tracking for both populations, and that was their outmigration timing out of these river systems. So ultimately, that led to this 6-variable state system that was quite a challenge to solve with standard value function iteration techniques, like similar to what we've been using. So just to briefly review those details, which we've already covered. And I apologize here, I'm using slightly different notation on these older slides. But just when I say pi, think about that as the reward, and where X is used, that's a state variable. So we've got this expected value of the infinite stream of discounted rewards, and our task is to choose a management action to maximize that objective. As you saw earlier this week, we can summarize this or restate this as a Bellman equation. And I wanted to point that out because we've got this value function here, which is then going to be plotted in the figure below, which nicely takes our infinite stream of payoffs, and note that it boils it down to a reward that we get in the current period, and then a value for being in any particular level of the state in the next period. So if we know what this value function is, then it boils this down to a simpler 2-period problem. We can think about our immediate reward and how that trades off with the value of having a given level of the stock in the future. So that might be, I might harvest some more, but that means I'll have fewer fish next period, and that value will be lower. Okay, so in the figure here is just an example of a typical value function where maybe it takes this shape over just this single state variable that I've shown here. So in value function iteration, which is this typical algorithm or one of the typical algorithms we use to solve this problem, we start off with, say, a rough guess of what that value function might look like. And we plug that in here, and then we make this decision for all of our states and look at what the optimal action is given the immediate reward, and that imperfect estimate of what the value will be for being at any given level of the state in the next period. And then we take those values together and update our estimate of this value function, which then becomes our new updated estimate. And we're repeating that process until we get to a final solution, where when we repeat this process of updating the value function, we don't get any further improvements to it. It has, quote unquote, converged. Okay, so notice that this is using the sort of backwards iterating technique, where you could think about this as the value sort of loosely speaking way in the future, and then we're iterating sort of backwards through time in some sense, and then arriving at a value function from today's perspective. And I say that because this approximate dynamic programming technique involves, instead of backwards iterating, more of a sense of forwards iterating. But it's going to share some of those features of value function iteration, including having some initial rough guess for what that value function might look like. So suppose in the figure below here, this simple linear function over the state is our initial rough guess for the value function. That is the value of being at any given level of our state variable. In this approximate dynamic programming approach, we use a simulation-based technique where we take a simulated draw of being at any particular level of the state variable, and then ask, we start off with a given level of that state variable, then we observe whatever sort of stochastic shocks might occur in this system, and then we choose an optimal action given where we currently are in the state space at that level of the state variable and that level of a shock. And that's going to take us to a particular level of the state variable in a future period. And given our current guess of the value function, we can say what the value of that is, and then also think about what was the profit from that decision that we just made, say the harvest, and get this updated estimate of what the value is of having started in that given state xt and making that decision and with the given shock. Okay, so this is the key here, that we get this new simulated observation of what the value might be for having been at that particular state. Then we can do that a bunch of times. So suppose the one that we just observed on the previous slide was this one. We can continue simulating and repeat this process and generate this cloud of points that you're seeing here, and then use some sort of curve fitting technique like regression to come up with our updated estimate of the value function. And then we just repeat this process until that value function again converges. That is, as we repeat more and more iterations, we're not seeing substantial movement in that function. Okay, so that was a quick tour of approximate dynamic programming, just very surface level, just to give you the basic intuition. So what are the advantages? Well, when we simulate forward in time, notice we didn't have to build that Markov transition matrix. We just used simulation. So we're using simulated draws from whatever stochastic data generating process we think is underneath this. If we're using integration to handle that instead of a Markov transition matrix, it eliminates the need for either one of those. So when we have many states and or control variables, simulating the process can be simpler and easier on our computing resources than some of these other approaches. What are the disadvantages? The code tends to be more complex than the standard dynamic programming, and it turns out that these are still under development, especially within natural resource management. And so there's still some art involved in tuning them so that you get a solution that looks reliable. So these are still under development. There's a couple of papers so far that I've been involved with that do this in a resource management context. There are some other flavors than the one that I just showed you for how to do this, including least squares policy iteration and policy approximation. These will be coming soon to a natural resource management problem near you and software package. So if you're interested in this kind of stuff, feel free to check in with myself or especially Paul. And then David is also working on some of this stuff. So if you're curious about this, check in with one of us and we can point you in the right direction. So that is all that I had. Let me turn things over to Iadine.
I think there's one question in the Q&A.
Sure.
Yeah, so there's one question here that says, does the number of stochastic points required still scale with the size of the state space?
Mike, before you answer, can you stop sharing your screen, please? If it's okay.
Yeah, let me just briefly reference a slide here.
Yeah,
so,
yeah, sure, makes sense.
So yeah, it turns out that as you know, so clearly the more points you have here, typically the better. But there's a cost to doing that. The more points that you have, the longer it takes to simulate those points, and sometimes the longer it might take to fit the new value function to those points, so that there is this trade-off between the number of points that you draw and the speed and precision of the solution. Let me stop sharing now to let Iadine pop in. And then of course, if you have not just one dimension of this state that you're concerned with, but multiple dimensions, you're going to have to take a much larger number of draws to then cover all those dimensions of the state space. So part of the art that I was referring to in implementing that method has to do with how do you think about intelligently sampling points, and how do you intelligently think about how many points you should sample in order to proceed quickly, but also reliably and ultimately with precision to get a precise, reliable solution in the end. So very good question. That gets right to the core of it.